All right, so let's get started then. So it gives me great pleasure to introduce Royal Society Research Professor Tim Palmer from the University of Oxford. And he is well known for, well, he's renowned in climate physics, uncertainty, predictability, and of course, chaos in the climate system. Today, Tim will be speaking to us about the future of weather and climate forecasting and whether we need a certain type center to kind of handle that going forward. Right? Thank you very much.
Thanks very much. So, thanks for coming. Nice to be here again. I was trying to think the last time I gave a talk in Leeds. I think it was about 15 years ago, and I think it was in the maths department, but I have to say my memory for these things is getting worse and worse. So anyway, good to be back. Yeah, I want to talk about the future of weather and climate. The new bit, I guess, of the talk is really at the end about AI. It's not so much work in progress as ideas in progress. So I want to promote or propose at least the new idea about how we might utilize the power of AI in our development of physics-based models. But I want to give a bit of a preamble, and in fact, a lot of the talk's going to be a bit preamble-ish about the issues, because I think these are important issues. Let's see. So just to start, you know, it kind of goes without saying that perhaps for most of us, I suppose, in the academic community, climate models are important tools for understanding climate. And an example I often use is if you have a physics-based model and somebody asks you the question, what role does Greenland play in the climate of Europe? It's a kind of in principle, at least, it's an easy question to answer if you have a physics-based model, because you just take Greenland out of your model, flatten it off, you could represent it with some ocean and just see what happens to the weather over Europe as a result. An AI model, you can't do that. I mean, it's training data, it's always seen Greenland. It's never seen a period where Greenland doesn't exist. So physics-based models are vital just for kind of getting basic understanding and for doing counterfactual experiments to try to understand what if something was different. But actually, that's not really what I want to focus on in this talk. It's the fact that they also are increasingly playing a vital role, I would say, in policy. And, you know, I've listed a number of things here. The issue of mitigation, for example. Well, how quickly do we need to cut our carbon emissions if we think there's going to be a major tipping point, for example, in the Atlantic thermohaline or some kind of Amazonian sustainable rainforest or something like that. So knowing, for example, whether there are going to be some sudden irreversible changes is vital for informing the speed at which we mitigate climate change. Adaptation. What does a country actually adapt to? Is it adapting to more storms and more floods? Or is it adapting to more droughts and heat waves? Because these would be very different types of weather. So we've got to have our models to know that. Otherwise, we could spend billions on adapting to the wrong stuff. The seasonal and decadal predictions are important in principle to help us become more resilient to immediate threats of droughts and heat wave and such like. And then something actually I've been involved in very recently at the Royal Society, looking at solar radiation modification. Is there a plan B? Can we spray sulfate aerosols in the stratosphere to offset climate change? The problem there is that at the regional level, you don't know whether you really are offsetting global warming. Changes in rainfall, you don't know that. You might actually be exacerbating problems. You know, who knows what's going to happen to the monsoons if you start putting loads of aerosols in the stratosphere. So again, I mean, models are vital, I would say, if we're ever thinking about this seriously. extreme event attribution. Anyway, the whole point is, you know, I'm not an economist, but surely this is worth hundreds of billions, if not trillions, to society if forecasts are trustworthy and accurate and reliable. And I would say, now this sounds slightly like a platitude, but I'm going to show you it's perhaps not quite such a platitude. It's our duty as scientists to say what we need to provide such predictions, or to say why we can't provide them if we can't. Okay, now with those grand words, I'm going to kind of start the scientific bit by just going back to, so you talked about chaos. I mean, my kind of, the way I kind of think about climate change at the regional scale was very much influenced by work I did, particularly with a colleague, Franco Molteni, at ECMWF, with just this very simple Lorentz 63 model, where we added some sort of forcing terms to the right-hand sides of the equations to see how the system would respond. And it kind of responds in an interesting way. So that's the famous Lorentz attractor. It's got these two regimes, and the, if you like, the internal variability of the model are just these irregular transitions between the regimes. And if you plotted a probability distribution for the whole attractor in state space, well, in fact, in two dimensions, two or three dimensions, you just see two blobs. So these are two maxima of probability. And the system is just making these transitions between these blobs. When you add forcing, what actually happens is that one regime becomes more populated and the other becomes less populated. The regime centroids don't change at all. They're very stable parts of the system. They're unresponsive to the forcing. So that the forcing can point in lots of different directions in state space, but basically the system responds by increasing the probability of one regime and decreasing the probability of the other regime. Now, for me, the take-home message from all of this was that, this was a sort of schematic of what was going on. So the cups are, you're dropping a ball bearing into these teacups, which kind of warm and cold circulation regimes, and you've got the span, which is the forcing. The key point is that the system is really susceptible to the forcing when it's in the most unstable part of the attractor. And if you could, in principle, fiddle around with that unstable part so that even though the system was forcing you towards the warm state, it actually responded in going to the cold state. And I'll show an example of that very quickly, how that can happen in reality. But the key point here is that the impact of the forcing is really determined by the dominant modes of variability of the system. And in particular, if you have a model which gets the dominant modes of variability wrong, then you're going to misrepresent how the real world responds to this external forcing. So what I'm saying is that this really, has strongly affected my thinking about climate change, that we can't just kind of ignore internal variability as noise on which the forcing is added like a linear system, because climate is non-linear, that's a fact of the matter. Rather, in this picture, getting the internal variability right is critically important to getting the response of the system to forcing right. Now, the dominant mode of climate variability is El Nino. And this is a picture, nice sort of satellite picture from January 25, where the SSTs in the El Nino region were negative. It was another La Nina year from a number of La Nina years that we've had in recent years. And we've known for decades now how El Nino and La Nina affect weather around the world. It affects the monsoons, in the Asian monsoons, it affects Atlantic hurricanes. And it affects jet streams. And for example, when there's a La Nina, the jet stream over the North Pacific and into the US is kind of displaced north, and California tends to be dry during La Nina. So, let me see. Yeah, so if you were to translate that picture from Lorentz 63 to the real world, the question is, how does climate change, the order one question from my way of thinking about climate change and natural modes of variability is, how does climate change affect the El Nino phenomenon? Does it make El Ninos more likely? Does it make La Ninas more likely? And if you can't answer that question, then you pretty much can't say anything about climate change on the regional scale, because pretty much everywhere in the world, I mean, probably the UK is one of the places which is least affected by El Nino. But for most places in the world, El Nino has a big impact on the climate, whether it's, as I say, in the Atlantic, Africa, Asia, North America, wherever. So I've been kind of interested in this question, how does climate change affect El Nino? Because the CMIT models are clearly doing something wrong. Because when we look at the 50-year trend, this is an example of where forcing the system to a warmer state, globally at least, seems to be producing a cooling trend, not only in the tropical East Pacific, but actually down into the southern oceans. If you look at the CMIT models, they don't get this at all. They see a fairly uniform warming, fairly featureless uniform warming across the whole Pacific basin. So either we're looking at this is some internal mode of variability which the models can't replicate, or this is the forced response to CO2 which the models are not getting right. Either way, something is going wrong, and that was made clear by a paper by Richard Seeger and colleagues a few years ago in the Journal of Climate. Now you could say, so what? But as I say, if you can't get this right, then I don't think you can say much about climate change. And in particular, everyone's familiar with the fires that happened in Southern California early this year, and there was a so-called rapid attribution report by the World Weather Attribution, which claimed it increased the likelihood of wildfire disaster. I think most of us have a kind of gut feeling that that was probably correct. But what does the science say about this? And I think this is where this report is really quite deficient. If you dig into the details of this report, what they're trying to do is look at how global mean temperature, both from observations and from the CMIT models, correlate with wildfires in California. And they've got various numbers here. But what really matters is this coloring. And the coloring, the light color, means that none of these correlations between global mean temperature and wildfire in California, either from observations or from the models, is statistically significant. Now, why isn't it statistically significant? It's because we know this, of course, that the immediate causal connection of the wildfires to the climate is through the cooling in the Eastern Pacific. That's the La Nina teleconnection that we've known about for decades. So if there is an impact, if there's a causal effect of climate change on the wildfires, it's coming through the effect of human climate change on El Nino, on this El Nino mode of variability, forcing it to the cooler La Nina state. It's not coming from global mean temperature, it's coming from this local cooling pattern. So when you do an observational correlation between global temperature and wildfire, you're not focusing on the right thing. And when you look at the models, we know that the models aren't getting the ENSO trend right anyway, so they're not going to get the right impact of climate change on wildfires. So although this conclusion might well be right, the science that we have it as we have it at the moment doesn't actually support that conclusion at all. Now, one of the really interesting things is that in very recent months almost, we're beginning to understand that this is a problem with inadequate resolution in the climate models. So this is a paper currently in review in the Proceedings of the National Academy of Sciences by the ICON group in Max Planck in Hamburg. Again, this cooling trend from observations in the Eastern Pacific, which I haven't pointed, so I don't have to do that. That's a sort of typical CNIP response, and this is a high resolution. This means kilometer scale in the ocean and maybe 10-kilometer scale in the atmosphere, as opposed to this, which is like 50 to 100 kilometers. There's almost, I mean, a bit of a pun, a sea change in the response. We've gone from warming to cooling. We're getting something close to the observed. So in other words, this is forced with the CO2, and it's responding by cooling in the East Pacific in the same way as the observations. So it looks like the cooling trend is indeed caused by climate change, but we need much higher resolution models to see it. And NCAR have a similar project called Mesoclip, and they've done an ensemble, and this is an ensemble mean over 10 members. And again, it's not actually as strong as in the ICON, but they're starting to get the cooling in their high-res models that failed to get in the low-res models. This is a paper by Tiffany Shaw and co-workers looking at various places across the world. I focused on this Eastern Pacific cooling trend, but there are lots of places around the world where the CMIP models are just not replicating the observed trends correctly. And I think that's entirely consistent with saying that if you can't get the right response of climate in your model, if you can't get the right response to El Nino, you're not going to get the right response to places around the world that are affected by El Nino. Okay, I'm going to actually skip over this slide because this is yet another reason why low resolution models are not doing a great job at the moment. And it's a thing called, the Met Office called signal to noise paradox. But again, I mean, people can talk to me about this afterwards. Again, I think this is a problem, again, linked to the inadequate resolution of climate models. So I'm going to skip over that. All right, so what I want to do is, if you could just sort of, look, I've just given you one example, which is El Nino. If you could just accept for the time being the premise that if we want to make our climate models really fit for purpose for these types of policy applications, we need to radically improve the resolution of the models down to, well, like the ICON model was a few kilometers. So let's call it kilometer scale. Problem is, as everyone knows, resolutions are incredibly expensive thing to computationally expensive. It goes, you know, at least as the third power, if not the fourth power of, you know, half resolution, then double resolution, potentially 16 times the cost. Change the time step as well. So, you know, we either say, well, okay, we'll just sort of like wait, you know, for computers to get more powerful and just hope for the best, or we try to think of some radical solutions for accelerating the development of high resolution models. So that's what I want to talk about. And I thought I would sort of talk about three quite different concepts. So, well, you'll see. Okay. So the first one is this notion that I should say, you know, my background's as a theoretical. My original PhD was in theoretical physics, so I'm kind of you know, familiar with all the stuff and the successes of CERN as an institute that has. I mean, we may not value the discovery of the Higgs boson as an important thing for society, but nevertheless, the Higgs boson would not have been discovered were it not for the fact that the nations of the world pooled their resources to produce a kind of a type of experimental infrastructure that would not have been afforded elsewhere. So, you know, one could envisage something like this for climate, that the nations of the world say, okay, look, you know, these are important things. We got to go back to all my things about adaptation and mitigation and solar geoengineering and stuff like that. We really got to have reliable answers. So why don't we pool resources in a similar way? So I've been banging on about this for like years and years and years. And it's had some successes. For example, this program actually, I mean, I organized a meeting at the Royal Society in the middle of the last decade, which led directly to a program called the Destination Earth Project, which is well, it'll shortly be literally €1 billion project on developing high resolution models. It's run partly by ECMWF and partly by the European Space Agency. Sadly for the UK, it comes under what's called Digital Europe. Digital Europe, whatever the word is, program, as opposed to Horizon Europe. So the UK is unable to tap into the resources of Destination Earth, which is a consequence of Brexit, unfortunately. My colleague Bjorn Stevens at the Max Planck Institute has kind of continued to promote these types of ideas through a project called Eve. And we had a big meeting in Berlin a couple of years ago on Eve. The idea being that, I mean, the core, if you like, would be some kind of dedicated exascale computing initiative. And the Eve project was perhaps moving it out from just a single CERN type of thing to maybe a few exascale hubs. But the point about these exascale hubs is that they would be 100% devoted to climate modeling. This whole concept has been received, I would say, in a very lukewarm way by the community. And I can kind of understand, like, lab directors who have been nervous about it because they see this as a threat to their own, well, preeminence. You know, take something like the Met Office, they would think, well, this could threaten our preeminence in climate modeling. But they're also worried, you know, it might, where would the money come from? Would it come from their own budgets? Would the governments be diverting money from these institutes to this international centre? So it's kind of been received rather, as I say, well, more than lukewarm, with no enthusiasm at all by lab directors. What has been disappointing to me is that the CMIP community have also been very extremely negative about it. And there I don't understand, because the systematic errors in CMIP models are there for everyone to see. So I have my theories about why they opposed it. I'm kind of, perhaps I won't say them out loud, but you can read what I say then. If you disagree, you can talk to me at, if you're a big CMIT model and you disagree with this, come and see me at coffee break and we'll talk. All right. I thought I'd just lob this one in because I don't know, I don't know how many people come with a physics background, but and a quantum mechanics background. Possibly not very many people. I mean, I have studied quantum mechanics for years and years, so I think I know as much about quantum mechanics as the companies who are marketing these things. And there's quite a lot of stuff online about how, I mean, hype, about how quantum computers are going to be fantastic tools in the future for things like forecasting weather and so on. And is this true? Well, okay, let's see. This is something I just very randomly found online. Some European company in 2025 has produced a computer with, the reason I've shown this is because it puts a number here, 50 qubits. So we all know in a regular computer, classical computer, the unit is a bit, it's a 0 or a 1. In quantum computers, it's a thing called a qubit. Now, don't ask what a qubit is, because nobody knows, doesn't really matter. But the point is that there are, if you take a state-of-the-art quantum computer, we're talking about 50 of these qubits, or qubits, whatever they are, there are 50 of them. Okay, now, the reason people are excited about quantum computers is that they kind of, they can solve potentially very complicated problems. And by complicated, I mean problems that have many, 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 many degrees of freedom. And the formula that you need to, the only formula you need to know is that when you have n qubits, you can solve problems with 2 to the power of n degrees of freedom. So if you like got a state space, you've got a model, the state space is 2 to the power n. Then in principle, you've got some kind of equation which could be nonlinear equation, which describes the evolution of your state in that 2 to the power n state space. Then with 50 qubits, that dimension could be 10 to the power 15, so 1,000,000 billion. So that's easily enough for a kilometer global climate model. So, as I say, what's not to like? I mean, is this going to be the future, quantum computing? We just throw our code onto the quantum computer, let it chunter away, solving Navier-Stokes and stuff, and then write out the answer after whatever it takes. Minutes, a few days, whatever, doesn't. Okay. Now, I wrote a paper in BAMS, Bulletin of American Metsoc, on this a couple of years ago in a postdoc of mine, where we talked about the good and the bad, well, and the noisy. But the good is precisely that thing. If you have 50 qubits, you have a humongously big state space. The technical word is Hilbert space, but we didn't worry about that. State space with which you can solve this equation. So that's all really good. However, there is an issue, and you never, ever, ever, ever hear the quantum computer industry talk about this. This is why I'm mentioning it here. Which is, how do you get the data out again from a quantum computer? Because in Fortran, or whatever your favorite language is, you just have a piece of code that says write x. X is some array, or some variable, or something. 850 millibar temperature around the globe. T. Write T. It'll spew out all these numbers on each grid point, or maybe plot it, something like that. So the problem is that there is no correspondence between classical computer languages and quantum computer languages. And in particular, there is no equivalent of this kind of line of code, write X. This is impossible to do on a quantum computer. What you can do on a quantum computer is ask the computer questions where the answer is yes or no. So you could say, is the value of x 0, 0 or something greater than 1? And it'll come back yes or no. The problem with that is that once you've asked that question, and you've got a 50-qubit computer, once you've asked that question, you have now only got 49 questions left where the answer is yes or no. And once those 49 questions, once those 50 questions have been asked, you've now destroyed, it's like whoosh, goes up in smoke. You've destroyed that information. There's not, that information no longer exists to be interrogated. So it's a kind of a weird concept, but that's how quantum computers work. So if you have 50 qubits, you can only ask 50 questions where the answer is yes or no. So if your objective is getting, I mean, never mind gigabits or petabits or anything like that, even if you wanted kilobits of data, no chance. All you can get out is 50 bits, 50 yes, no's, 50 zeros or ones. And that is the absolute roadblock, in my view, in our view, to the application of quantum computing to any big data problem like weather and climate. So in a nutshell, unfortunately, no chance whatsoever. So let me move on to the third possible route, which is AI. And interestingly, the first paper I'm aware of applying AI in weather forecasting was actually done at ECMWF in the early 1990s or mid 1990s by a Frenchman called Frédéric Chevalier, who noted that one of the most expensive parts of the parametrization scheme of any climate model actually is the radiative transfer part of the code. And he proposed replacing the radiative transfer with a neural net, which had been learnt on a kind of line-by-line calculation of radiative transfer. For reasons which are never clear to me, it never actually made it into operations at ECMWF, which is a great shame. But a kind of sort of ultimate version of that Chevalier thing was published in Nature last year by, well, the lead team is from Google in the US, but actually there are two of my ex-students, Milan Klover and Sam Hatfield, and a postdoc of mine, Peter Dubin, are also co-authors. Now, I mention this because what I'm about to say is I don't think what they're proposing here is the right way forward. So I feel a bit bad about this because these are some of my ex-students here. But I'm presenting this to actually suggest this is not the way to go. But basically, so what in the paper they call this neural GCM, so a like physics-based model, but based on neural nets as well. And the idea here is that we keep the dynamical core of the model. I'll say a bit more about this shortly. But all the subgrid parametrisations, all of them now, not just radiation, absolutely everything, all the subgrid tendencies are kind of, all based on neural nets having been trained on suitable observations. So is that a way, and the idea is, yeah, this could be a lot faster. So is this a way to high resolution kilometer scale modeling? Well, in order to answer that question, I want to just spend like few seconds on going back to real basics here. So one of the equations that we attempt to solve in a physics-based model is the Navier-Stokes equations, nonlinear partial differential equations. And of course, these are the fluid equations of turbulence. And these equations have interesting properties. And one of them, at least if it's an incompressible flow, this is only approximately true if it's a compressible flow, but a fully incompressible flow, as was proven in the book by Maida and Bertotti, these equations have a kind of scaling symmetry, which means that if you have a particular solution of these equations, you can kind of create a whole one parameter family of solutions with this parameter tau, which scales time and space, and the pressure field similarly. So this is a scaling parameter. And what this basically does is say, if you're, or what it's trying to kind of describe mathematically, is that if you have a turbulent fluid, the turbulence is, extends down to arbitrarily small scales as you zoom in. So there's a kind of, there's a power law structure to the fluid. And we've known this for years. This is observations of the real world from Nystrom and Gage, going back many decades now, showing that if you plot the kinetic energy, zonal wind, meridional wind, as a function of the scale or wavelength, you plot it in logarithmic space, you basically get straight lines. So you actually get two straight lines, and the slope of the straight lines has a crossover point at around, I don't know what this is, few hundred, well, meridional, few tens of kilometers. I mean, the thinking is that for these very large scales, the flow is highly constrained by the Coriolis effect, which makes the flow very two-dimensional, and that gives you this k⁻³ spectrum. And when you go to smaller scales, the flow becomes less constrained by rotation and becomes more three-dimensional, and then you get the sort of standard Kolmogorov scaling of k⁻⁵. Anyway, that's the point, that this power law stuff is a you could say it's a consequence of this scaling symmetry. Now, if you solve the equations numerically, so you stick in a truncation scale explicitly into your numerics, then manifestly you have violated the scaling symmetry, because you've whacked in something, which upscale of that, you've got Navier-Stokes. To the other side of it, you've either got nothing or some parameterized formula. So you're clearly doing some violence to the scaling symmetry when you solve an equation numerically, solve the Navier-Stokes numerically. So in a sense, this is the ultimate origin of errors in climate models. It's not the parameterizations per se, but the fact that you are truncating your equations. So it doesn't kind of matter what if you have any kind of parameterization, is going to give you systematic errors. That would be the message from this slide. So what does this mean in practice? Well, if you have what you'd like to think is the case, if you were somebody that that develops parameterizations and believes very strongly that parameterizations are good things and accurate things, what you'd like to think is that if, say, you're trying to parameterize convection or something. So here's a grid box. You'd like to think that convection occurs in on scales which are typically small compared to your grid box, and you've got lots and lots of these things so that you can treat the convection as a kind of an ensemble of processes, and the parameterization then is a kind of bulk formula for the effects of all these convective plumes within your grid box. And in a way, it's supposed to mirror, the way in which we derive things like molecular viscosity, molecular heat conduction, heat diffusion, in statistical mechanics. However, what this power law structure is telling you is that the world actually isn't like that. It's more like this. There's a whole spectrum of scales. We do have some very small scales, but we've also got some medium scales, and we start to get scales which are comparable with the grid scale. In fact, we might even have scales which are larger than the grid scale. And in a sense, this is fundamentally unparameterizable. We'll come on to something. I argued that one way of ameliorating this process is to treat the parameterization in a stochastic way, not as a deterministic formula. But that's only a kind of an approximation. I think it's a better approximation than a deterministic formula, but it's still an approximation. Now, a key point I want to emphasize here is that, because there's this kind of spectra of scales, this kind of power law of scales, the coupling, if you think about, say, convection, the coupling to the large scale, to the result scale flow, isn't solely at the grid scale. It extends out across a range of scales, the super grid scales. So if we're really going to think about coupling unresolved processes, it's not just coupling at the grid scale, it's coupling across multiple space and time scales. So any scheme that brings, English isn't right, so we've got, anyway, any scheme that uses AI-based, so coming back to neural GCM, because the neural GCM, kind of interesting as it is, it's still basically saying, this is all the subgrid scale stuff that's been learned by a neural net, and it's coupled into the GCM just at that subgrid scale only. So it kind of falls foul of this idea. And I think, and I haven't seen any evidence to contradict this, that neural GCMs will suffer the same systematic error problems that any GCM will do. Sure, they might be able to calculate the parameterizations faster, but they'll have the same problems. So what's the solution here? So this is something, so many years ago, almost 30 years ago, or something, I gave a talk at ECMWF when I was working there. This kind of started the whole stochastic parameterization work. But I was kind of trying to promote alternative ideas in thinking about parameterization. And one idea which appealed to me a lot at the time was thinking about convection as a cellular automaton. Cellular automaton. And the idea here is you have a, if you like, you have a grid which is much, much, much finer, or much finer than your model grid, your GCM grid. And these cells are supposed to be like convective cells, and they're either on or off. So it's like one bit. There's one bit of precision in the cellular automaton. Now you can have rules. For example, you could calculate how much convective available potential energy there is in a grid box from the result scale flow, and that could determine the probability that a cell was on or off. And then you could have cells, sort of neighboring cells, if they started to become adjacent to each other, the lifetime of the cell, or in other words, the probability that they both stayed on in the next time step would increase. So you have kind of longer lasting agglomerations of cells. and the idea here would be that this will be a kind of like an organized convective system. And one of the things I really liked about it was that you can very easily encode rules for how these cells, if there's a mean wind, so you're in the tropics with let's say an easterly wind, the cells could advect with the wind. So in principle, subgrid information then can move across the grid boxes from one grid box to another. And obviously in a regular GCM you can't do that, because the only way subgrid information can affect a neighboring grid box is through the large scale, through the resolved flow. So the subgrid would inform the large scale, then the large scale could affect that box, and then that would go down to the subgrid scale. But here we've got potentially information propagating through grid box boundaries without any thing. Now, this actually, the big problem with this at the time was that these rules for how the cellular automata would evolve and things were a little bit ad hoc. And, for that reason, people were unsure, I suppose, whether this is a good thing or not. One person who did work a lot on this was a lady called Lisa Bengtsson, who moved to the US, and she's Swedish, moved to the US, and she works for NOAA. And these types of CA schemes have been coupled into some of the NOAA weather forecast models. But the point I'm raising here is a conceptual point, which is that this is not a proposal for a parametrization of convection, but in a sense, it's a proposal for an extension of the dynamical core itself. We're trying to kind of, represent albeit in a very simplified way, the process of convection. So this sort of snapshot is not. It's obviously not it's not like an average or bulk formula. It's a particular potential realization of convective plumes in this, whatever this part of the world is. So it's different from a parametrization. It's sort of an extension of the idea being it's an extension of the dynamical core downwards. I should say in Lisa Bengtsson's work, what she did was to add kind of Newtonian relaxation terms into the resolved scale model from the average. So, for example, here there would be, to say, take this blob here, it clearly projects onto grid scale average wind, temperature, rainfall in particular, in this grid box here, and this one and this one. So this actually would have an effect on these 4 grid boxes, and that would get coupled into the large scale flow through relaxation terms, which would be driven by the CA. So you've got a kind of two-way coupling now. So the cape affects the probabilities of the cells being on, but the cells themselves can feed back to the large scale flow. Just a couple of minutes. Okay, yeah, I need to finish. So the question is, moving forward, rather than ad hoc, could we learn rules for these CAs from information, from observations? So yeah, so just in the last 2 minutes, I want to talk about a very practical project that we've got going in Oxford, which is to downscale the ECMWF IFS forecast to the subgrid scale, the regional scale over East Africa. We're doing this for the Met services in Nairobi and Addis Ababa. And we have an AI based on a conditional generative adversarial network, which produces rainfall. It's trained on satellite iMerge, satellite rainfall data. It's more skillful than IFS. And the forecasters are getting ensembles every day. But the point I want to make is that what I'm starting to think about now is this idea of taking these downscaled rainfall and wind and temperature forecasts and doing basically what Lisa Bengtson did with the cellular automata, but now with a full AI model of feeding it back to the IFS model itself. Well, this could be done at quite low precision, so it's feasible. So the idea here is, neural GCM wants to sort of use AI in the parameterization part of the model, and I'm saying no. Instead, use it in the dynamical core. So we have the explicit Navier-Stokes, like on the maybe down to say 10 kilometers, and then AI emulated Navier-Stokes down to kilometer scale or more. As I say, to even say this is work in progress is perhaps putting it too strongly. We're starting to think about, got a student, and we're starting to think seriously about doing experiments for testing this idea. So we'll see. Okay, so all right, time to finish. I hope I kind of convince you we do need to radically accelerate the development of high-resolution physics-based models if we want these models to be relevant for policy, and I think surely they must be relevant for policy. CERN for climate change, I really wish we could do this, but it seems so politically difficult that I'm not particularly optimistic at the moment. Quantum computers, no chance, absolutely no chance. Don't even think about it. I say this because some Met services around the world are recruiting people to develop, quantum, weather models on quantum computers. This will never work, I can absolutely assure you. It's a waste of money. Better off using those people for doing something more useful. Combining with AI, yeah, maybe. I think there's some interesting ideas here, but not to improve the parameterizations, but rather to extend the dynamical core. So that's what I am going to certainly be thinking a lot about in the coming years, and that could be an interesting way forward. So thank you.
Great talk. So open it for questions.
So I have a question about how do you train AI, AI because like the great problem of AI sometimes the scarcity of data, because AI has a lot of data. Like you're thinking training on the results of simulation, or
no, I would train it on observed satellite data. So yeah, that was a picture of a of a satellite. So you can kind of pixelate all these. If these are convective clouds, you can kind of pixelate them, and so when the coarse grain model is predicting a certain convectively active region without getting the structure bit right, the AI would pick up on the detailed structure, and so feeding that into the model, you would get you would correctly represent this mesoscale structure, and then the idea is you'd feed that back into the model, the dynamical core itself. So it could all be done on satellite observations. Now, a question sometimes people say, well, yeah, but in climate change, are you being constrained to the present? There's some interesting work. We were talking about this over lunch of in AI weather forecasting. People have taken out, say, Category 5 hurricanes, and the AI can no longer forecast Category 5 hurricanes. However, if you keep the Category 5 hurricanes in, say, the Pacific Basin, the AI seems to be clever enough to learn from that to predict Category 5 hurricanes in the Atlantic, even though it's never seen in its training data Category 5 hurricanes in the Atlantic. So as long as the training covers sufficiently, extreme events that occur today, it should in principle do a reasonable job at, if these extreme events become more likely around the world, as long as it's seen those extreme events somewhere in the world, it should be able to kind of extrapolate to other regions if these events become more likely. So it's not obvious, at least to me, that that is a problem. But obviously, all these things have to be looked at carefully.
Yes, James. Could you maybe expand a little bit on the difference between determinant parameterization and AI learning?
Well, I guess what I'm saying is in a regular parameterization, you just say, oh, here's a grid box. And there's stuff going on inside the grid box that I don't know. So I'm going to try and represent it. I'm going to try and represent that tendency, that subgrid tendency, by a formula or some piece of AI. So I've done that grid box. Okay, good. Now I'll move to the next grid box, see what's going on there, add another tendency. And then in time, I might, okay, I've done this tendency for this time step. Now I come to the next time step, do it again, do it again. What I'm saying is that in practice, with this scaling symmetry, the coupling of the subgrid to the large scale is not just at that one grid box. It's across there's a spectrum of space and time scales that have to be coupled in a dynamically consistent way. So you'll have to do it over many time steps and over many spatial scales. I mean, that's, for example, why in the stochastic parameterization, which we worked on back in the 90s, it was vitally important for the stochastic noise to have a spatial and temporal autocorrelation, which took it over several grid box and time steps. So you weren't just injecting a different noise at each grid box and time step. So that's a kind of poor man's way of incorporating. I mean, stochastic was a poor man's way of incorporating this coherence. But yeah, that for me would be the kind of key difference, that you're not just taking each grid box at a time and somehow quasi-independently feeding it in information, but you're coupling it across a range of time scales and spatial scales, which somehow, well, maintain the power law structure. I mean, that would be the test, that it maintains the power law structure.
Guess what I mean? Where is the AI part or the AI?
Oh, as I say, the AI would be. I mean, the simple conceptual picture is to think of that cellular automaton. So that's too simple in a way, but it gives you a kind of conceptual picture. And say, I mean, I could take this satellite map and again, as I say, pixelate it like with ones and zeros. So where there was some cloud, I give it a 1, and where there was no cloud, I give it a 0. And I'd learn the rules for evolving the individual cellular automata from these pixelated satellite images. And I would let the AI, I wouldn't choose the rules, I'd let the AI choose the rules that would, evolve the cellular automata and kind of, increase the probability of agglomerated cellular automata from the pixelated satellite data. That would be the AI's role.
And how would that be represented in the grid model? Some smaller grid that has some sort of limiting simple grid based on the rules, you could just produce numbers properly. What's learned into a grid.
Well, it would. I'm not sure I understand that exactly.
Well, because you are simulating something at subgrid level.
Yeah.
That's doing it. Is that doing it?
You'd have some simple rules. Yeah, the neural nets would give you some simple rules between inputs and outputs, and that would.
Then that goes into the equations before.
Yeah, I mean, like matrix multiplications and things like that may be measured. Yeah.
I think.
Well, look, I mean, I don't necessarily understand it that well myself because we haven't actually worked in detail through an example. But as a matter of principle, I think I can see this working. But yeah, I'll come back in another 5 years and tell you if it worked.
Last question for Andrew.
It's a really interesting idea, and I can see this working potentially convection, where you've got the observations. You can argue about how good ICAS is. You've got potentially got high resolution observations. But at what point do you stop? Do you do the same thing for turbulence, where you don't have the observation?
Well, I did in that paper in '96. I did actually look quite closely also, because the other thing which I've been quite interested in over the years is topography, how to represent subgrid topography. Because one of the problems, again, with models is if you have a sharp, like if you imagine a hypothetical mountain range, let's say, which was very narrow but quite high, it can block the flow. In reality, it would block the flow. I mean, things like the Rockies and the Greenland, actually, since we were talking about Greenland. I mean, that can block the flow. And if you average, so take the Rockies in particular, if you average the coarse resolution model, that kind of relatively sharp range of mountains over a forced grid block, the mean height decreases. And then for the model flow, the model doesn't really see that topography as an obstacle. It just flows over and get weak velocity waves. So I did think quite a lot about implementing cellular automaton schemes for actually topographic, kind of representing topographic corrections. Because there has been quite a lot of work, in cellular automata, how they respond to flow around, blocking obstacles. But turbulence, look, I mean, there's no question. I'm not. Perhaps I should have said this. I'm not trying to, my goal is not to develop a model where there are no parametrisations anymore. I mean, that's utterly unfeasible. That will never happen. We're always going to need it for things like, ultimately turbulence and radiative transfer and that sort of stuff. Cloud microphysics, all that will continue to be parameterized. But the idea is that the big things like deep convection, like topography, and perhaps in the oceans, the big mesoscale mixing, eddy mixing stuff. We need to do better than just these parameterizations, because they really are important to the large scale flow. So if this could be a way of getting at least those processes much better represented, but still keep parameterizations for the really small scale stuff, I mean, that will be an improvement, I think, big improvement.